Hello, everyone. Welcome back to my Coding Everyday journey. Today is day 37. Today's a Friday, February 21st at 12:31 p.m. So today I'm going to be looking at these graph problems here, and then we're going to be doing number of connected components in an undirected graph. So I haven't looked at this problem yet. The title is pretty indicative of what we'll be doing. There is an undirected graph with n nodes. There is also an edges array, 0 to n minus 1, and then return the total number of connected components. So I don't know what connected components means. I don't know if it's just like, so if you have like 0, 1, 1, 2, I think these are connected components, so this would be 2. So let's look at the test cases here. So 0, 1, 0, 2. So if we have 0 is connected to 1, 0 is connected to 2. So my guess would there would be one connected component. Okay, 0, 1, 1, 2, 2, 3, 4, 5. 0, 1, 1, 2, was it 3, 4, 2, 3, 4, 5. Okay. So now here, I think we have one component here and another here. So the answer should be 2 here. Okay. Okay, so I think this one's pretty straightforward. So basically we, for every node, I guess we just DFS through it. So we'll say for I in range n will DFS. So if I not in visited, then we'll DFS I, and then count plus equals 1. So here we're going to DFS through every node. If it's not in visited, we'll start DFSing it and add all of them to visited, and then our counts will go up by 1. So it's kind of like number of islands. It's very much like number of islands. So if we DFS something, then we know the count goes up by 1 if we call it here. Okay, so then we'll define DFS. We'll also make a visited set here. I guess here. Okay, so this will take in a node. Okay. So all we want to do is just go through it. So we'll say for neighbor in graph of node. So we still have to build graph up here. For neighbor in graph of node, if neighbor not in visited, then we can visited dot add neighbor and then DFS neighbor like this. I think that's it. So let's build the graph. So the graph, we have edges, so we'll say graph equals dictionary. For edge in edges, I'll call two nodes ij equals edge. So, and I guess what we could do is use, we could set them all to 0 here. So I empty list or I in range n. And then we'll just say graph of I dot append j and graph of j dot append. Okay, and then visited, of course, we actually want to start it. So visited empty set, but when we start the DFS, we want to say visited dot add I like that. And then we will return count. Okay, let's see what that does. Okay, awesome. Sweet. So that was 5 minutes. So let's look at another problem. Yeah, this one is pretty much just number of islands, except instead of a 2D array, it's a it's an adjacency list, I think. And let me just make sure the runtime should be v plus e, right? Yep. Okay. Redundant connection. Okay, so this will probably be the... Oh, this one looked really hard. I've seen this one before. Okay, let's just try it. So this one looks good. Let me just comment it out. I mean, I don't really need to say that that's DFS. I'll just say like DFS every node. Visited. Okay. All right, let's look at this one. We're given an undirected graph with n nodes labeled 1 to n. Okay. Initially, it contained no cycles of n minus 1 edges. We have now added one additional edge to the graph. The edge has two different vertices chosen from 1 to n and was not an edge that previously existed. The graph is represented as an array of edges of length n. Okay. So everything's pretty standard. So basically we have an undirected graph with no cycles, and then they add an edge that makes it a cycle. I don't know if it has to make it a cycle. I guess it does. Okay. Return an edge that can be removed so that the graph is still a... Sorry, I had to sneeze. Return an edge that can be removed so that the graph is still a connected, non-cyclical graph. If there are multiple answers, return an edge that appears last in the input array edges. Okay. That might be handy if we do DFS, because then we can just do the first one we encounter maybe. Okay, so let's look here. So our input is 1 to 2, 1 to 3, 3 to 4, 2 to 4. Okay, so one of these was added. We don't know which one, so we have to return the one that was added. Okay. And then we have 1, 2. So let me just draw this graph here. So 2, 1, 3, 4, 5. Okay. So I'm noticing we basically have to so locate cycle, and then we have to remove an edge in the cycle last in list. Okay, so first let's locate the cycle. So this is perfect because I did a similar problem yesterday when you have to graph if it's a valid tree, and you have to locate a cycle of an undirected graph. And I was going to redo it, but I think I can do it for this one. So first let's just locate the cycle. So this is a cycle check of an undirected graph right here. Okay, so first let's build the graph here. So I have some experience with that now. We're not given n. Is there n edges? Yeah, okay. Length of edges. Okay, and then for ij in edges, graph of I dot append j, and graph of j dot append I like this. Okay, so let me print graph. So I did this, the other problem I just did, I said, instead of ij here, I had edge, and then I said ij equals edge, but you can just do it in the for loop. So I think this is a little bit better, makes a little bit more sense. So let's look at our graph. Okay, so we don't have 4. 4I in range length of edges 0, 1, 2, 3. Okay, so I think we want 1 to length of edges plus 1. Okay, 1 is connected to 2. Let's look. 1 is connected to 2 and 3. 2 is connected to 1 and 4. 3 is connected to 1 and 4. And 4 is connected to 3 and 2. Looks good. And then this one. 1 is connected to 2, 3, 4. 2 is connected to 1. 3 is connected to 1, 4. 4 is connected to 1, 3, 5. And 5 is connected to 4. Looks good. Okay, looks good, looks good. Okay, so we have a graph. Now we want to DFS through the graph to find a cycle. Okay, so this will take a node and its parents. And we're going to start. So the reason you need the parent is, so to detect a cycle in an undirected graph, so you're going to explore, you're going to basically DFS, and if you ever encounter anything that's visited, then you know that you're in a cycle. But the problem is, so if we go to 1 and then 3, so let's say our DFS goes here first. So 3's neighbors are, so 1 has, let's say it was 2, 4, actually let's say it was 3, 4, 2 for some reason. So we look at 3 first. 3's neighbors are 1 and 4. So when we check 1, 1 is invisited, but it's not actually a cycle. So with undirected graph, remember it's like this. So we basically just don't want to include this way here. We don't want to go back. So what we can do is store the parents and just omit the parent from indicating a cycle. So that's why we pass this here. So for the first node, we can start with any node. I'll just start with 1, and then I'll set -1 as the parent because we just came in from nowhere. Okay, so what we'll do is for neighbor in graph of node, if neighbor not in visited, so we need a visited set. We'll just put it here. Okay, if it's not in visited, then we'll say visit.add neighbor and DFS with neighbor, and then its parent is node, the one we just came from. Okay, so if it is in visited, then and it's not the parent, so else if neighbor does not equal parent, then we have found a cycle. So print cycle found. So there will always be a cycle found. So let me just print at node. Okay, so now this should cycle found at node 4. And let me just see. So the edge basically. So 4, 2, that doesn't make sense. Oh, we're in the wrong test case. 4, 2, 2, 4, 1, 3. Okay, so it's not all of them. 4, 1, 1, 4, 1, 3, 1, 4. Okay. Another thing I have to do is I should add 1 to this set here. So like this. Just because we explored 1 first. Okay. Okay, and yeah, and once there's a cycle found, we're not. Okay, so now this is the hard part, is what to return. So let's just say right now this will return true if there's a cycle and false if there's not. So here, okay, so if we get to the end without returning anything, then that means there is no cycle. So here we want to say if, okay, so here we return true, there is a cycle in this DFS. Here, if that DFS was true, then we return true. So if I print DFS there, it should give me 2 trues. So true here, okay. And now let me see if let me say edges equals a list of lists. So I'm just going to build a little test case here. And then if this equals 2 to 3, so there should be no cycle in this graph here. I think I made a mistake. So n is, I think with these parameters, it like has to be, okay, instead of doing this, I will say graph equals 1 is connected to 2 and 2 is connected to 3 like this. I forgot my comma. So this should work, because if we have 1 is connected to 2 and 2 is connected to 3, it should just look like this. So what is wrong? For neighbor in graph of node. Oh, because it has to be 2-way. I'm just doing 1-way. So 1 is connected to 2, which means that 2 is also connected to 1. 2 is connected to 3, which means that 3 is also connected to 2. Like this. Okay, that should fix it. Okay, false. So there's no cycle. Okay, so I think that's a cycle detection right there. That's great news. Okay, so now what we want to do is maybe instead of returning true or false, we could return the edge that we found that cycle. So let's just experiment with that. Okay, so we want to return an edge. So I'm trying to think, if I have a tuple, well, I guess I could have just an empty list. So we could return, so here we could return empty list, and here we could return okay. So if neighbor does not equal parents, then we should print node, we should return node neighbor. And then if this has any value, we should return it. We should return it. Whatever this gave us, we should return that. So let's say so like edge cycle, or I'll call it cycle edge. If cycle edge, then return cycle edge. Like this. So here we'll either get a empty list, or excuse me, we'll either get an empty list here, or we'll get a list containing an edge. So if it's empty list, we'll skip it. But if it is a edge, we will return that edge. Okay, so let's see. I got rid of the graph, right? Okay, so we output 3, 1, which is one of the results. And then here we output 4, 1. Wait, 3, 3, 1? Yeah, so 3, 1 here is a cycle. So that's good, but we have to return. Okay, so we've figured out. And then let me just double check with here. So here's 4, 1. Okay, so we have successfully returned. If there is a cycle, we are returning one of the edges in that cycle. We now, though, need to return a specific edge, the edge that appears last in input edges. So what I'm going to do instead, so I think what I want to do is see how the program is sort of executing here. So if I print, still not muted, okay. So if I print, let's just say node equals here, maybe I can trace the order in which we are. Okay, so here in the first case, we're going 1, 2, 4, 3, and then finding 3, 1. So is there any better way? So 2, 4. Alternatively, what we could do is I think there might be a way to make it. So right now I'm trying to engineer it so the first cyclical edge we encounter is the last in the input list. Alternatively, maybe we could just like store every cyclical edge and then find the one that comes in last. Like search if this one's in that and then if this one's in that. So that it would be O of n, which would be fine. So we'd have a set. Okay, so this might be simpler. So we'd have a set of all edges that cause cycles, right? Like this. So let's say that these 3 edges cause cycles in our graph. Then we go through the edge input list in reverse order. So we'd say for I in range -1, actually not -1. Actually, would it be -1 here? Yeah, so it would be -1 length of, no, it would not be. It'd be length of edges -1, stop at -1 and go backwards. So we do this, and then if edges of I in this set, which I'll call like Q for some reason, if it's in Q, then we return E of I. So this would be linear. But I remember before I was having a problem where it was not detecting all of the. So this is assuming if we can obtain Q. So if we could obtain Q, I could solve the problem using this method. But there might be some trick where you can just, the way that you explore it. So 1, 2, 1, 3, 3, 4, 2, 4. So this builds the graph. So I don't know if I don't think it's possible to build the graph in such a way that this works. Okay, so let me figure out how I can maybe try to build Q, because the problem is okay, I'm having some ideas. Okay, so let's look at this example here. So the problem is for us to revisit an edge. So if we have 2, 1, 3, 4, 5, like this. Okay. So we'll visit, so let's say we start at 1, right? So then we visit 2, One's also visited. So, right, so we have 1, 2, 3, 4. Okay, so when we visit 2, there's nothing. When we visit 3, 3 has 1 and 4, so 1 is the parent, so we don't count it. Then we visit 4. Okay, and then 4 is connected to 1, 3, 5. So 1 is something that we've already visited. So but we don't want to stop there. So I have an idea, actually. So we don't want to stop there. We actually want to keep going. So is it like, do we only want to stop if we visited something twice? But then the problem is we would just go back to 2 again. Because I want it to be like, okay, so 1 goes to 2, that's dead. And then, okay, let me try something. So let me just keep track of the number of times that we visit something and see if I notice any patterns, because I feel like this is related here. And then 5. Okay, so here we start by visiting this once, then we visit 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 this twice, this twice, this twice, this twice, this 3 times, this 3 times, this 3 times, this 3 times. So we'd be infinite here, which would be fine. But this is, we don't want this. Okay, so what if we keep track of, so what if we have a like cycle set maybe? And okay, so our cycle set starts off at 1. We explore 2. Our cycle set at this point is 1, 2. But there's nowhere left to go, so we backtrack to here, and our cycle set is 1 again. Then we go here, our cycle set is 1, 3. Then we go here, our cycle set is 1, 3, 4. And when I say cycle set, I mean if we visit any of these nodes from this node, that means there's a cycle. So then we visit 1, and we've identified a cycle. So now the cycle set is still 1, 3, 4. So maybe we should, so then we can use this to determine the cycle. So maybe if we, okay, different, okay, so I was thinking, what if once we get the cycle set, we can use all those numbers. So now I'm thinking of a counterexample to that. So let's say we have this, okay? So here the set is 1, here it's 1, 2, here it's 1, 2, 3, here it's 1, 2, 3, 4, and here we run into 2, which is in our cycle set. But we shouldn't use all of these numbers because 1 is not part of the cycle. So maybe when we get to here, we only want to explore nodes that are in our cycle set. Okay, so what if when we find a cycle, okay, so let's keep this here. So 1, 2, 3, 4. This is our cycle set. So now we're in a cycle. So what if we reset our cycle set to 2? Then we, well, there's no way to distinguish 3 and 4. In this case. It works in this example, but in this example it does not. Because I was thinking we could only explore things that's in our cycle set, But the problem with that is well, okay, new thought. So when we have our cycle set, maybe when we arrive at the node that caused the cycle, we can eliminate everything before that node because we know it's not part of the cycle. So for instance, in this example, right, we'd have 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. So maybe instead it's a cycle list. Okay, and then we run into here with, so our cycle set is 1, 2, 3, 4, and we encountered 2. So that means we should cut off everything before this, and then everything after this is the nodes in our cycle. And then we can just get all edges in between these nodes and remove the last one. So this will generate Q. Okay, let me see if this would work. Here. Okay. So here our visited set is 1. Here it's 1, 2. I'm going to start calling it a cycle list. Okay, so our cycle list here, because the order matters in this case, is 1, 2. So then we backtrack, so we remove 2. And let me just make sure this would work. So if we also have, like, let's say 6 here, so our still not muted, so it'd be 1 and then 1, 2, and then 1, 2, 6. So we're out here, so we're going to remove 6. So we can append to a list and pop from it. Then we're out here, so we're going to pop that. Okay, then we're at 1. Here we'll be at 1, 3. Let me just delete this. Here we'll be at 1, 3. Here we'll be at 1, 3, 4. And then we explore 1, which is in our cycle list. We get the index of that and cut everything before it. Okay, so this would work, I think. And it would be very similar even if we had like another node here, like 7. It would still work because we'd have 1, 7, 1, 7, 3, 1, 7, 3, 4, and then we encounter the 7 with 1, 7, 3, 4. So that means our cycle has to be these 3. And then using this, we can go through the graph and we can see that 7 is connected to 3, 4. So then we can populate Q basically. Okay. What if the cycle is 4 edges? Okay, so let's look at, and then I'll start coding it. But I just want to look at one last example. Sometimes I think I have a habit of I find an interesting solution and I just keep going with examples before I actually code it, which I don't know if that's a good thing or not. Okay, I have to get my color game going. All right, so let's say 1, 2, 3, 4 like this. Okay, so here we have 1, and then 1, let's say 1, 3, 1, 3, 4, 1, 3, 4, 2, and then we encounter 1, so we know that all of these are in the cycle. So our graph is 1 is connected to 2, 3, 2 is connected to 1, 4, 3 is connected to 1, 4. So 2 is actually 1, 4, 3 is also 1, 4. And then 4 is connected to 2, 3. So now how do we get from this all the nodes in the cycle to all the edges in the cycle. Because what if 1 is also connected to, let's say, 5? So here would be well, maybe what we could do is just run through like all the connections of 1, all the connections of 3, all the connections of 4, all the connections of 2 until we find something that's, well, maybe what we could do. Okay, another thought, and I think this might be useful to think. So in this case, right, we actually know the nodes that are in the visited set, or in the cycle. So we know the nodes that are in the cycle. So what if we just, so we have our cycle set. So instead of doing all that overhead stuff, so we know that in our cycle list, it's 2, 3, 4. So we'll convert it to a cycle set. And then we'll explore the graph. We'll basically just DFS the graph and keep track of all the edges in our cycle. And that should give us Q. So we'll convert cycle. All right, yes. So then once we have Q, then we have the answer. Okay. So that's my thought. And remember, Q is a set of all edges in the cycle. All right. Okay, so we have, so let's have a cycle list. Okay, so I'm going to get rid of visited for now, and it should be a list. Okay. All right. So here we want to say cycle list dot append neighbor. So in this case, we'd append 1, for instance. And then after we DFS that, we want to remove it. So cycle list dot pop. Okay, and then let me just so if it's not in cycle list, if it is in cycle list, well, so this is O of n though, if we're checking the list. I mean, we could also have a cycle set. And it has to be a list. Okay, so I'll also have, let's say, cycle set. So here we'll say cycle set dot add neighbor. So basically one of them is for lookup and the other is for order. So cycle set dot add cycle set dot remove neighbor. In this case, it's just okay. Let's say cycle found with cycle list equals that. Okay, sorry. All right, let's see. So cycle, another typo. Cycle list. Okay, so then what we want to do is okay, so we found a cycle. So now we want to say, so what did we just encounter? So neighbor, so first elements so first cycle num, or yeah, num. So let's get the index of neighbor. So cycle list dot index of neighbor, and then we want to take cycle list only after that neighbor. So cycle list equals cycle list spliced at first cycle index, like that. So we only take the, all right, so let's see this here. Cycle, and we want to stop the program. I'm just going to put exit for now. Is it printing anything? Node equals 1. Is it because I'm doing this? Let me just comment that out and see if that's the cause of it. Yeah, so that is the cause of it. Even though I exit the program? Does that not work? Cycle list. Oh, is it because I'm... Is it because I'm assigning? So this is now in local scope. Okay. So if I did this, it would fix it. Right? No. Wait. Is there a way to do this in place? I mean, I could just call it a different variable. Let's just say like temp cycle list. Do you have a spelling? Oh, is that what was happening? Okay, now I don't print anything. Okay. Okay. So it doesn't seem to be cutting it out. Okay, so let's say print cycle found with so we'll say node neighbor. Still unmuted node. Okay, let's see what this does for us here. Node 3 neighbor 1. Okay, so that means, so 1 goes to 2, goes to 4, goes to 3, goes to 1. Okay. So our cycle is 1, 2. So it's 1, 2, 4. So it's actually going 1, 2, 4. Wait, so it's not popping correctly. Because here it should be... It should backtrack, right? cycle list. So it's not backtracking properly. So shouldn't it get removed? I guess not. So 1 goes to 2. And then we go to 4. 2. So it has no neighbors, but it is DFSing. So should I just say if something... So I think my backtracking thing is incorrect. I was hoping that when we get to this point, like when we go back, it would just remove itself. So if all of its neighbors are visited, then we should remove itself. So is there an easy way to check if all of its neighbors are visited? Or if it has no neighbors. So here it just... So this has no neighbors. Oh, so it's returning empty list. Should I say it down here? I feel like this won't work, but... Yeah. Okay, so my problem is, so when node equals 2, it has, well, it does have a neighbor, actually. It does actually have a neighbor. This neighbor is 1. If neighbor not in cycle set, so then that's just going to skip. And so it's just going to skip. So it's still skipping. Maybe we can say here if neighbor... I don't think that's going to change anything. Actually, I know it's not going to change anything. I wonder if I should go back to what I had before, where it just returns true when there is a cycle. Maybe it's because I'm popping. Check. Okay. All right. So what if I have 2 different things here? So I'll just get rid of this. So cycle. So I'm going to try this. Cycle dot add neighbor. Cycle dot pop. So visited will always keep going. Cycle. Okay. Just fixing some bugs. Okay, so my backtracking is not working. I don't know why. Is it because I'm saying pop? Okay, so I want it to remove when node equals 2. I mean, I guess it makes sense why it's not being removed. So if we have 1, 2, it's still going to go through every neighbor before we even hit this. So when we call DFS here, then DFS of 2 goes nowhere because it has no parents. So DFS of 2 gets filtered out. So after DFS of 2 got filtered out, should we not remove 2? Removed neighbor from cycle. So we add neighbor. So we add neighbor 2 to cycle. Okay, and then here exploring neighbor 2, adding 2 to cycle. And then what happens after we add 2? And then we DFS 4. Yeah, basically this problem is it's simplified to, can you find a cycle in a graph and find every node in that cycle? So if I could just get it so that if we had 1, 2, if I could just get it so when we explore 2 and our cycle is 1, 2, that it deletes itself back to just 1. Because what's happening now is it explores 2 and then it instantly goes to 4, and it only removes it after all of our neighbors have been visited, after they've all been DFS'd. What if I try it iteratively? So we say while stack node equals stack.pop. We say for neighbor in graph of node if neighbor not invisited. This might work actually. So if neighbor not invisited, then we stack.append neighbor. I remember there was a problem just like this where you had to do this. So we could append neighbor visited.add neighbor. So I mean I could do it like the way I don't want to do it, where in a stack I could store, like I could just store here cycle set, and then when I call it, okay, so before we worry about efficiency, let's do it this way. So cycle set, okay, so if it's not invisited, then we append cycle. So what we should say is cycle.add neighbor, and then cycle I just don't get why it's not working recursively. I mean, I'm guessing this won't work either, because it seems to me like it's the same sort of logic. Okay, so we'll have stack equals. So what is this? It's a number and a set. It's a number and a set. Stack is a list of tuples. Cycle. Okay, I didn't print anything. What do I even... I guess I'll just print all the nodes that get popped and make sure the DFS is working first. Okay, 1. So it adds 2, 4, 3, then it pops 3, 2. Is my graph wrong or something? Okay, so it added 2 and 3 to the stack, then it popped 3. 3 adds 4 to the stack. Pops 4. 4 doesn't add 5. Oh, I'm looking at the wrong example. I wonder how long I've been doing that for. Oh my gosh. I've definitely been looking at the wrong example for a long time. That's bad. I wonder if what I was doing was actually working and I was looking at the wrong example. Okay, so here 1 adds 2, 3, 4. Then it pops 4. 4 adds 5. 5 gets popped. Stack is just 2 and 3. Stack is 1, 1, pop 1. 1 adds 3 and 4. Stack adds 2, 3, 4. 4 gets popped, 4 adds 5, 5 gets popped. Five got popped, so now okay, this looks a lot better. So if neighbor is in cycle, then just say cycle found at forgot the F. Okay, we're at 1 hour. 4, 3. Wrong case again. Okay, 4, 3, 5, 4. Alright, honestly, I'm gonna try this again and look at the right test case. And just see what happens. So what are we doing right now? Okay. Cycle set. I don't want that. Okay. No attribute add. Cycle.add. Other test case. Oh my god. It was working the whole time. It was working the whole time. No. No. Alright. Well, it's a good reminder to make sure you're looking at the right test case at least. Alright, so the problem is not done yet though. So here it tells us we found cycle. I just want to know the cycle set that we have when we find the cycle. I just want to make sure that it's the nodes wrong test case. Yeah, cycle 134. Okay, so now, but the problem is, let me do a different test case like what I was talking about before. So if we have 1, 2, 3, 4 like this, so 1 is connected to 2, 2 is connected to 1, 3, 4, 3 is connected to 2, 4, 4 is connected to 2, 3. Okay, so I'm expecting this one will actually be incorrect. So it doesn't matter what test case I look at. Okay, cycle found with node for neighbor equals 2. Yeah, so it went this way, this way, this way, this way. Hey, there's a cycle. Okay, so now we want the cycle list thing that I was talking about. I can't believe I was looking at the wrong thing. Okay, so cycle order dot append neighbor cycle order dot pop. So that's cycle, and let's now look at cycle order, and we want cycle order to be initialized to 1 as well. Okay, it doesn't matter the test case. Cycle order is 1, 2, 3, 4. Okay, so now when we find this, we want to do what I was doing before, where so we'll just say index of last in the cycle is, well, what we can say is, actually, let's just keep it simple. So index of last is cycle order dot index of the last one we found, which is neighbor, I believe. And then we say cycle order equals cycle order starting at index of last. I think I might have had the colon incorrect too. Okay, it doesn't matter the test case. Okay, can't associate. Yeah, so this is the scope variable that I tried to fix before. Okay, cycle order 2, 3, 4, which is 2, 3, 4. Okay, so cycle order gives us everything in the cycle. Let me get rid of this, and I'll check both test cases. So test case 1, it should be all of them, and test case 2, it should be 1, 3, 4. Yeah, 1, 3, 4. Okay. Okay. So when we first get here, we want to basically exit the program. So I think we can do that by saying, so we'll just return empty list. Here, we will return cycle order, which is a list. And here we'll say, if this is anything, then we will return, okay, so say out equals this. If out is anything, then we will return it. All right, so now let's print f out equals, and then we'll call that function, which should return out. Okay, so first test case, 1, 2, 3, 4. Second test case, 1, 3, 4. Okay, so I'm going to change this to get nodes in cycle. So this works. I wonder if there's a better way. Maybe instead of using a list and a hash set, we can use a dictionary that we could totally replace that later. With just a dictionary, I think. That basically just keeps track of the order. So it'll be like value to index instead of index to value. All right. Okay, so now we have all the nodes in the cycle. So now we are going to say, I don't want to call it queue, I'll say edges in cycle equals empty set. All right, and now we'll say we are just going to DFS, or I guess I could just do an iterative one here. We're just going to DFS this graph one time. That's it. So we'll say, yeah. Okay, so visit equals set. Stack equals, okay, so we'll say random node, or I guess we could just say start node. Start node equals, we return cycle order, right? So if I print cycle order here, because it's a non-local variable, it should be the same. It's going to give me an error though. It's not going to compile. Okay. So instead I'll just say here cycle order equals get nodes in cycle 1, -1. Okay, perfect. So we'll say start node equals cycle. Start node equals cycle order dot pop. Visited is going to be a set of just start node, and stack is going to be a list of start node. Okay, while stack node equals stack dot pop for neighbor in graph of node. If neighbor not in visited. Okay, so we only want, so if neighbor not in cycle set. Okay, for now I'll just say cycle order, then continue. So we only want ones that are in the cycle order. And we could say if it's in visited too. And then if it's not in visited, then we can say edges in cycle dot add node neighbor and visited dot add node. No, neighbor. Okay, so if neighbor not in cycle and neighbor not in visited. No, if it's in visited, we want to continue. Okay, so let's print edges in cycle. we can't add a list. Let's just add a tuple then, set of tuples. Okay, case 1, it's giving me 3, 1, and 3, 4, which is not true. Case 2, it's giving me I'm not adding to the stack. Where am I printing stuff, by the way? Just here? Huh. I wonder why it's giving me those false ones. Infinite loop. Oh, or. Okay, first example. 3, 1, 3, 4, 4, 2. It's not giving me 1, 2. Okay, and then this example. 4, 1, 4, 3. It's not giving me 1, 3. I just have a feeling that it could be this. So regardless of whether the neighbor is visited or not, we would add it. Okay, that well, this is for case 1, right? So it gave us 2, 4, 1, 2, 2, 1, 3, 4, 3, 1, 4, 2. But it didn't give us 1, 3. But it did give us 3, 1. Okay, let me put this here, but maybe it wants neighbor node or something. 3, 1, 3, 4. Does the order matter? Like if the answer is 2, 4 and I return 4, 2, does that matter? Because we're supposed to return an edge, right? So I think the order doesn't really matter. Okay, I mean we could put this. No, because why am I missing the first one? It has to do with this somehow. Edges. I need something in edges. The first neighbor. Is it the first thing that gets explored? Maybe? If it's the first thing that gets explored. Okay, so for test case 1, it's what? Okay, so for test case 1, it's 3, 1? Am I missing something? Why is 3, 1? Node should be 1, no? Why is node not 1? Oh. We start at 3, I guess. It's not guaranteed that 1 will be in there. Oh, okay. So 3, okay. So 3, 1, 3, 4, 4, 3, 4, 2, 2, 4. No, 2, 1, 2, 4. So 3, 1, 3, 4, 4, 2, 2, 1. So it's not adding the last one. Sorry guys, my brain is like so cooked. I think I could have definitely solved this one, but I spent like 30 minutes losing all confidence and deleting my solution because I was looking at the wrong test case. 1, 2, 4, 3. 1, 2, 4, 3. So 3, 1. Is it this? No, because I reset it. So 3 is connected to 1 and 4. So it takes 1. And then 4. Okay, so it's 1 and 4. I think I just like forgot how DFS worked for a second because yeah, you still you add everything to the stack before you pop. But it's so weird because with the recursive one, you don't really do it that same way, right? Because you just, this one's not here, so you just DFS this one. And then you backtrack here after the stack is done. So, I mean, it's the same order, but it's a little different because you manually add it to the stack with iteratively. Okay. 3, 1, 3, 1, 4. Also, too, now it's like the parent thing. I'm almost wondering if I should just do this. What am I even trying to do anymore? Okay, so I have the edges in the graph. So all I want to do, so let's say I have 2, 3, and 4. All I want to do is explore. I want to DFS starting from 4 and only explore the edges that are in that. Why is that so hard? All right, so all right, let's get rid of that. Test case 2. So 4. All right. So let me bring up the diagram. Okay, so 4 goes to 1, so we should add 4, 1. 4 goes to 3, we should add 4, 3, which we do. Now 3 goes to 1. But 1 is already invisited. And then 1, 3 goes to 1, 1 goes to 3. Why do we... Okay. So I'm just going to say here, edges in cycle dot add node neighbor. And not here. Yeah. So then this will give us all of them. Okay. Now... I can solve this problem. It's just like so scuffed at this point. So now we have edges in cycle. So what I want to do is convert every tuple to a list. But you can't have a set of lists though. So my whole plan with Q is kind of wrong because I can't have a set of lists. If this was a tuple, I'd be fine. So now I could do n squared where it's like, I mean, there's just a lot of things I could do here, but I don't know if it's really the best way to do it. So these are all the edges in the cycle. We want to say, hey, is this in here? All right, I think we could do that. Okay, so for I in range, length of edges, that's the input, right? Length of edges, -1 to -1, backwards. Okay, so then we'll map. Yes, okay, I could do this. So edges of I, let's map to, say, some variables A and B, right? Where A is the node, let's just say node and neighbor, because, right, node and neighbor. And then we'll say, if node neighbor in edges in cycle, print found node neighbor, and we would just return edges of I here. Okay, let's see if this works. Found 2, 4. Found 1, 3. Why is it 1, 3? 4, 5. 3, 4. Okay, so it should be 3, 4. We have 4, 3. All right, then we'll say if neighbor node found 2, 4. Found 4, 3. Okay, so we want it. Okay, so that should hopefully give me the right answer. 2, 4. No output. There's no output, people. What is going wrong? Another typo on cycle. That's like the 40th typo on cycle. 2, 4. 3, 4. All right. So in this case, let's just return node neighbor. And then, is there a -1 or something? Okay, we got it. All right, this is... All right, so my biggest takeaway from this problem, I know I have a lot to work on with this code. My biggest takeaway from this problem is when I am debugging, make sure I'm looking at the right test case. Because for those of you who missed it, I was debugging, I had a solution which ended up being correct. But for like at least 30 minutes, I was looking at test case 1, but expecting the result from test case 2. So I thought it was not working, and I thought my solution wasn't working. And I was confused, and I deleted it, and I like restarted, and then I realized I was looking at the wrong test case. And I was like, then I had to go back, rethink about everything and like why it was working. Because I remember I just didn't understand why it wasn't working, but and it was working. I was just looking at the wrong answers. So this, it's basically just code slop. But I could probably clean it up. Definitely. So instead of using, so this part is a function that I made which gets nodes in a cycle. I think what I could do instead of using a list and a set is I could probably just use a dictionary. So it has O1 lookup, and then I can use the values to this index thing so I can get the order. Yep. And then this part, basically, once I have the nodes in Okay, so this part gets all nodes in cycle. So find cycle and returns all nodes in the cycle. This part gets all edges in the cycle with, using nodes. I don't know if there's a way to just get all the edges right off the bat without getting the nodes first. That's just the way I thought of doing it. And then here, basically just find answer using edges in cycle. So that's the order. Like, it kind of makes sense. This builds the graph. It's only clean part of the code. Yeah, so this, but hey, I mean, at least I got the answer and I didn't give up. And yeah, I'm definitely just going to keep redoing these problems until I'm really comfortable with, because yes, I'm solving them, but it's not really like, so technically I'm done with graphs, but I think I'm going to keep revisiting these, because yes, I'm solving them, but I'm not doing it in the best way and I'm not doing it quickly, which is for graph problems as they get harder, understanding the in and outs of traversing and how to detect a cycle, like that stuff needs to kind of be automatic. So, I'm getting there, but yeah, I mean, at least I solved it. And I didn't know like an algorithm or anything. I just kind of pieced it through. Yeah, like I said, biggest takeaway for this one, look at the right test case when you're debugging. And with that, thank you guys very much for watching. This was day 37. See you tomorrow for day 38.